I'm Mr. Fido at Intel. I've got the T-shirt. I'm the FIDO, the TSE rep for Intel. And I've been working on FIDO for about 2 years, and I'm greatly enthusiastic about all things FIDO. So one of my colleagues, I'm supposed to know everything that's going on, right? That's my role. One of my colleagues called me about 2 weeks ago, and he said he's based in the PRC and he's working on Proxy. And he said, listen, I won't make it to Copenhagen. Can you do my talk? And I went, okay. And he said, because you're really familiar with everything I'm doing, right? And I went, yeah, sure. So I picked up Hong Jun's talk. I'm far from an expert in this field. I actually feel it's a kind of owning up time because I've got Pierre sitting in the audience who I know is an expert in this field. And I'm wondering why I'm here and you're there. There's obviously been some, maybe, yeah, anyway. So here we are talking about Proxy. So you'll have to forgive me having notes in front of me. So clients don't talk to pods directly. There's a layer of indirection. And in some cases, there's multiple layers of indirection between clients and pods. What clients have is a stable IP. A stable IP that represents a service. And a client knows if I talk to this IP will let me talk to a service. And typically they get that IP through some DNS mechanism. A service is really roughly composed of an IP front end, a stable IP, and then a set of pods which increases and decreases as the application scales up and scales down on the back end. There's a notion of a controller. And what the controller does is it talks to Kubernetes, and I have more deeper dive slides on this in a minute. Controller talks to Kubernetes and understands and reflects when pods get added, when pods scale up and scale down. So how does it work today? Well, Linux kernel takes care of a lot of the indirection through what I heard recently described, and I like this so much I'm going to repeat it, which it's called a duct tape of networking that is IP tables. If you ever have a problem, I'm pretty sure you can fix it somehow in IP tables. So, you end up with this kind of split. You end up, and this way, in some ways, the term kubeproxy is kind of a misnomer. So when you're using the default implementation, what kubeproxy actually does is it sits and talks to the API server, understands that pods have arrived, and adds IP table rules for them, and understands when pods go away and removes IP table rules. So you can kind of attribute, say, the kubeproxy is kind of the control plane that programs the data plane, and the data plane is IP tables. The IP tables implementation is typically what takes care of the load balancing. IP tables implementation, the kernel is typically what takes care of the load balancing. The kernel is typically what takes care of the natting as well. And there are other implementations. You don't have to use the kernel implementation. I'm also going to talk about kubeproxy here. There are other ways of doing it. I saw some nice material on that. Oh, hello. Oh, it did do, that's right, the very, very original implementation. And then I saw one speaker say, and then we improved it so much that we moved it to IP tables. But you're right, it was actually a proxy originally. And back in those days, it used to bounce traffic from the kernel up into user space, and then from user space back down to the kernel. And IP tables allowed it to keep it all inside the kernel. My colleague Hong Jun has prepared a slide on how he feels about that, which you can kind of take as the left-hand side is kernel slow, and on the right-hand side we have the VPP-based implementation, which is fast. But they covered the most important point here is, I'll pick them out, is that what we have in VPP, or when you use the VPP implementation, it gives you access to things like memif. So memif, I think Damien, who are not here, Damien and Konstantin are going to talk a little bit later on, is our high performance interface into containers. So this proxying methodology, this load balancing methodology works seamlessly with memif. We also take advantage of what I was talking about earlier with Konstantin, which is the very, very, very good scaling in VPP. Everything we do in VPP is designed for scale. This load balancing implementation that we're talking about, KubeProxy, is no different. We've designed it to scale out quite well. Anything else to say? No, nothing else to say. So, it's a proposed architecture. I kind of covered it a little bit earlier, but you typically end up with the controller piece, which sits and listens to Kubernetes API, sits and listens to Kubernetes, watches as pods arrive and watches as pods leave, and then programs the data plane implementation in VPP to do the address translations, to do the load balancing between the virtual IP and the pods. But that's not all we do. We support, because sometimes there's multiple layers of load balancing at work. There's load balancing between nodes, and there's load balancing within the node itself. And we take care of both pieces. So we implement both the node level load balancing, depending on whether you're using the cluster IP to identify your service, or whether you're using the node port implementation to identify your service. But we also take care of the external load balancing, and I'll get deeper dive into that later, where you want to load balance between the different nodes. We also take care of the connection tracking, and we get into that a little bit more deeper later. And then we also take care of the NATing. Oh yeah, we handle both IPv4 and IPv6, and we take advantage of, I like to refer to FIDO VPP as a Swiss Army knife of networking, in that, many of these things are pieces from VPP that we are actually reusing. So we reused the maglev load balancer implementation that was already in VPP to create KubeProxy, and that was work that Pierre did and a number of the others FIDO team. We also reused the NATing implementation, very scalable carrier-grade NATing implementation that we have in VPP. So, this all wasn't written from the ground up. It's a really great example of how you can bootstrap a new network function very, very, very quickly in VPP. We're able to reuse NATing, we're able to reuse load balancing, and make changes specifically to work with Kubernetes. So everything's connection orientated. So you need guarantees that when a connection is always going to flow between a same client to the same pod. So you need a consistent hashing methodology to make sure that connections always flow the same way. But this is particularly hard to achieve as new pods arrive and new pods go away, that traffic always flows the same way. And this is kind of a little bit of the heart at what we're doing. So we have a strategy. So we basically have a two-part strategy to achieve even distribution between the pods. And then we record the selection, after we've achieved the even distribution, we record the selection in a thing called a connection table to make sure that the traffic always flows the same way. So you end up with two tables. You end up with a flow table, and then you end up with a connection table. The connection table records the way traffic was flowing, and the flow table is used basically to count how many connections each pod is serving. So you get an even distribution between pods. So the flow table is used to realize an even distribution between pods. The connection table is used to record which way the connection going, from which client to which pod the connection was flowing. So within the flow table, we basically it's a token bucket implementation in which that you basically you add a counter to as a connection is assigned to each pod. You use a hash. You use the hash to look up the flow table, and that gives you a selection of pods. And then you look at the least contended pod, and that is what that's the pod that you select. You then go record that selection in the connection table so that the next time a packet arrives for that connection, you can look up the connection table, identify, okay, the connection was made from this client to this pod. No need to look up the flow table, and the traffic flows directly. Anything else to say about that? Oh, there's some advantages to this. Okay, I think turn on the next stage. Okay. Consistent. Why isn't it moving on? There we go. The advantage of this is each pod will receive almost the same number of connections, basically by counting tokens. When the set of pods changes, it's highly likely that your connection will always flow back to the same pod, go back to the same pod. With the flow table is recomputed. Whenever the set of pods backing a service changes, the flow table is recomputed. But what the consistent hash guarantees is that it's very, very likely that your client will always be talking to the same pod, unless that pod, of course, has gone away. So we have a VPP API, we have a VPP CLI, where you can specify the natting address ranges. The basic flow is as follows. When the packet comes in, it's load balanced first, and then we do destination NAT. When the packet's on its way from a pod, way out from a pod, we do source natting and then egress. So this is an important point I want to touch on, and I talked about it a little bit earlier, which was that in VPP we are able to take with KubeProxy, we're able to take care of both the load balancing that happens on the node itself for cluster IP and node port, but something else we really want to that's really important is we also can take care of the load balancing that happens between nodes. And this is actually we have a project in this area that I'm going to be able to talk about a little bit more later this year, I hope. But this idea that you can act both as the cloud native load balancer on the node itself, but then also act as a kind of a discrete load balancer appliance that load balances between the pods. Okay. Okay. So. I don't see a load balancing between nodes and within a node, right? Kubernetes today, the client, the load balancer chooses. Sure. So what often happens in Kubernetes today is, particularly with the within a service, is that a packet can arrive in a node, and then that node can decide, I'm not going to service that request on the current node, and then you end up what's called a double hop. The traffic. Yes, virtual IP. Yes. Mm. So when you talk about load balancing, you focus on the external service. Oh yeah, I'm talking about external service. So so what often happens is you can end up with a kind of a double hop between a node to another node. Now, another way to approach that is to turn that off, and you say local only. You can only local load balance between the pods on this given node. Well, then you need something in front of it, and in some cases you might use something like the Amazon Elastic Load Balancer or something like that, an external service to do load balancing between nodes. And that's my point is that VPP and kubeproxy can act as both these things. And you're right, it's all for external traffic. Apologies if I breezed past that. But it gives you the ability to load balance between the nodes and then load balance between pods on the node itself. And it's the same technology used in both instances.
So yeah, I haven't done a lot of work on this external service case. In that case, where is the first load balancing? I mean, how would it know?
Well, when the packet first arrives on the flow, it comes and it does a load balancing externally and decides, computes the hash, and then finds out which node is the least contended based on that hash, and then sends the traffic that way. And then you do the same thing at a pod level on the actual node itself. Mm-hmm.
Right? You're not running VPP and ELD. The ELD doesn't know where the backends of a given service are. It doesn't know enough to send the SYN
Mm-hmm.
request to a node that happens to be running one of the backends.
Mm-hmm.
One of the endpoints, right? One of the servers for this particular service.
So, I'm sorry, could you repeat that?
Yeah, I mean, I'm sorry, I may be speaking garbage. Am I correct?
I don't think you are. But go ahead.
Right? If you're using some external load balancer,
Yeah. You think it doesn't have enough information?
how would it know where the servers are for this service, and how is it running VPP? It's an external thing.
Okay. I see what you're saying. Okay, so in the kind of deployments that we look at is that you provision an external load balancer yourself. You're provisioning it yourself, and you engender it with the same set of knowledge. Except in this case, it's a set of knowledge is the set of nodes that it needs to load balance between. Set of loads that it needs to load balance between. So the external load balancer understands that there's a set of nodes it needs to load balance between, and then the node level load balancer understands there's a set of pods it needs to load balance between, and that's essentially how it's happened. But in both cases, you have to program. At the node level, it needs to understand I have this set of pods, and at the external level, needs to understand I have this set of nodes. Does that make sense?
Yeah, that's half of it. The other half is if it's external, I didn't get to choose to make it run VPP.
So when I say external, I mean just don't mean on the node, and I'm here extolling the virtues of VPP. So of course I'm going to say that your external load balancer needs to be based on VPP.
Just to close out that point, so normally external load balancer is a load balancer outside the cluster
Mm-hmm.
that the cloud is providing to you.
Mm-hmm.
So here you're talking about VPP implementing a separate outside of cluster load balancer.
Yes.
In addition to the in-cluster load balancer.
Yes. That's my point, is I can service both functions. Okay. Oh, okay. So I think I covered. Yeah, I think I covered this. Just to close out is that we built upon the very, very good work that was already done in VPP. There was a maglev load balancing implementation already available in VPP, and we introduced a number of optimizations. One optimization to it, and that's in terms of in basically making the algorithm a little bit more efficient for this particular use case. Mm-hmm.
Maglev does a number of other things. Which subset of maglev is in VPP?
So I'd encourage you to talk to Pierre Pfister, who's sitting right next to you, who wrote the maglev load balancer in VPP, and he'll be able to give you the full readout.
Well, you could just say quickly, but So when you say VPP has magnet load balancing, what specifically it is? Well, he uses or the hashing similar to magnet. Is that yeah, the load balancer part of pseudo random the hashing logic, consistent hashing as we're getting the connection table, all that. It's the data plane. Yeah. Because VPP is only a data plane. So you have the data plane part of magnet. You don't have all the orchestration around it. The hashing logic is similar. I think I see what you mean. It has other stuff as well.
Yeah. I think there's a difference between the algorithm, the maglev algorithm, and then the implementation. I think that's what you're poking at. And just to close out, so what we have, and what we're really trying to realize with the kubeproxy implementation is a high-performance way to load balance in the cloud in user space. We're at the point now where we're looking at doing the integration with Kubernetes, making it easier for Kubernetes to consume. It's got a number of benefits in that it load balances very well. Load balances almost evenly, very evenly between pods, and it also remembers your connection state to make sure that traffic always flows a consistent way. Okay.
All right. Any other questions? I think the microphone is behind.
Ed's got it.
There's a surprise.
Make sure it's not a hard question.
No, but it's actually an orthogonal question. I was just curious. All the time you said there you're using NAT plus load balancing.
Mm-hmm.
Any chance of using overlays plus load balancing?
Actually, I kind of breezed past it a little bit earlier. So here between the external load balancer, the VPP external load balancer, we actually use GRE tunneling into between the load balancer and the actual the node itself. Is there any chance of using overlays? Yeah, I would answer yes. I think it's something we should look at. Go ahead, Ed.
Are you supporting direct server return in the way you've done this?
Are we supporting direct server return? I think that's a question I can't answer.
So you probably can if I give you a little better description of what I mean.
Okay.
So the really, really big breakthrough that maglev made was direct server return. Because if your client is smart enough to deal with the GRE packet, then when whoever is load balancing gets something to the VIP, you can send it addressed over that GRE tunnel to where it's being handled, and it gets handed to whoever's providing the service, still with the original VIP IP in place, which means whoever is providing the service can then send the packets back, and they just go directly. So you only end up load balancing the forward traffic towards the server.
And that's all we do. We only load balance on ingress. We don't load balance on egress.
Okay, so you're not natting at all then. You're delivering with the VIP.
Yes. So
perfect.
We are natting. We're doing a destination map on natting on the way in, and we're doing source natting on the way out.
Okay. Have you considered doing just sort of the pure maglev style with no natting? Because that's enormously more efficient.
I think Pierre's.
Here is the GRE tunnel. That means if you're using GRE tunnel here, that means that you're not natting. So I think you're getting confused between the two different modes that you have. One is the external, which probably does GRE tunnel, and which. Yeah, well, inside in the service proxy, you need to know what the VIP is. Yes,
we're doing the natting at the node.
I'm not sure how it works exactly in this case.
On the way into the cluster and natting on the way out of the cluster, but we're not. We're only We're not natting on the external load balancer at all. That's just load balance. That's just load.
I think what you will find is that when you actually get to integrating this up into something that is. I think what you will find is when you get to integrating this up to something that is aware of the game you're playing, then the fact that almost every app in the world is going to be listening on 0000 means that you can do direct server return, which means you can save yourself a huge amount of CPU cycles burned into the double natting.
Oh, okay.
But for that to work, you have to have a CNI plugin that will actually do the right thing in setting that up.
Okay.
So it gets to the integrated service piece.
So in that case, I think you can do direct service return because you have GRE tunneling.
Yes.
In the other case, I think the reason why you don't do it is because you couldn't use tunneling, and so you decided to. Ongjun decided to go for a NAT because that's what's done today, and because having a tunnel might have consequences on deployments.
This just reinforces the point that I thought you should.
Let me just make sure I understand the tunneling here. The question I'm asking myself is, where is the tunnel terminated? Is it inside the pod, or is it on the host of the node?
No, I think it's terminated on the host, is my
So
understanding.
the host decapsulates, and it can't send to the VIP then. It has to send to the pod's particular address, so the pod cannot do direct service return.
It can if you have something that's actually smart enough to handle its piece, right? So you're right if you're just handing stuff to the kernel and the kernel has no idea what's happening. But if you've got, for example, the ConTVP stuff in there where you can be smart enough, then you can do the direct server return.
Okay, actually that brings me back to my overall question about the talk, just make sure I understand what's going on here. So you're talking about how to build a service proxy using pieces from VPP, but you're not saying that the connection between the service proxy and the pod is anything smart or great. The service proxy still turns around and calls the kernel to deliver the packet into the pod. Is that right?
The service proxy, well, no, we actually use Mammoth or vhost user. So we have, and that's going to be talked about in a moment. How the packet actually gets delivered in the pod is through an efficient memory interface, an efficient user space memory interface. So the packets typically don't bounce back into the kernel. It's delivered by a high performance raw packet interface, which which Maciek and Damien are going to talk about in a little while.
Thank you.
Are we done with that topic? Can I switch over to something else?
I was going to say we are running behind time. Is this maybe a question we want to take out to a conversation we want to take to break, or is it a question we should ask the kind of with the larger room here?
I'll just make a quick statement.
Okay.
I'll turn it into, it was a leading question that I know the answer to. So instead, I'll just jump to it. You say that maglev delivers almost an equal number of connections over the whatever you're balancing. Yes. And that's true. It's a very nice consistent hashing function. But you can still have clustering of those connections over time. So you can, with just basic maglev, end up with getting unlucky with your connections, and you end up overloading one server versus another. I mean, this is just something that you can.
I sense, Mark, that you may have the answers to this.
Come to Pierre and I's talk at 16:25 on Wednesday, and
so
we'll talk about that.
You had a question. Really, what you meant was self-advertisement.
I was plugging our session on Wednesday afternoon.
Just so we're all clear on what exactly the point of your taking the microphone was.
That's it.
All right, and with that, we can go to break. We are sort of behind time, so let's try to take a shorter break and be back in here in 10 minutes. And then we will pick up with a talk on ARM support within FIDO. Oh, and let's give Ray a hand. Thank you.